Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the isentropic process. Let's firstly talk about the general conditions of isentropic process. By the definition of entropy, that is, equation 116, we have expression for the isentropic process. According to the first law of thermodynamics, we have the following expression. Therefore, we have the expression shows that as long as the heat released by the thermal system to the surrounding is always equal to the heat production or generation, which is from the work loss, the process is isentropic. Generally speaking, the isentropic process refers to frictionless adiabatic process, that is. Secondly, let's talk about the definition of isentropic process. The definition is a process during which the entropy remains constant is called an isentropic process. For example, the process performed in steam turbines, internal combustion engines, and compressors are similar to isentropic process. We mentioned earlier that the entropy of a fixed mass can be changed by 1. Heat transfer and 2. Irreversibilities. Then it follows that the entropy of a fixed mass does not change during a process that is internally reversible and adiabatic. For example, during an internally reversible adiabatic process, the entropy remains constant, that is, S1 equals S2. A substance will have the same entropy value at the end of the process as it does at the beginning if the process is carried out in an isentropic manner. Thirdly, let's talk about the process equation and state parameter changes. The process equation is, which can be derived from the third ds equation, where gamma 0 is the specific heat ratio, also denoted as kappa, known as adiabatic index. Can you derive the above process equation? The process equation can be derived from the isentropic process of the ideal gas, that is, the third equation of ds. Let's show the derivation of the isentropic process equation for ideal gas. Recall the third ds equation. The third ds equation can be solved based on the exact expressions of the partial differentials from the ideal gas equation of state. Therefore, we have the following expressions of isentropic process equation. Fourthly, let's talk about the relations of isentropic process. Based on the process equation, we have the relations for the properties and also the changes of internal energy, enthalpy, and entropy. Firstly, let's talk about the PV and TS diagrams. These are the isentropic process shown on the PV and TS diagrams, where path 1 to 2 is the expansion process and path 1 to 2' is the compression process. Pay attention to the slope of the isentropic path line in the PV diagram and try to derive it. Actually, it can be found from the second ds equation directly. Sixthly, we come to the calculations of work and heat. Calculations of work are done for the isentropic frictionless process by the ideal gas with constant specific heat. There are two types of work, expansion work and technical work. We have two methods to determine the expansion work. Technical work then can be found from expansion work. The expansion work from the first method. The expansion work from the second method. This means the expansion work is identical to the internal energy decrease. Review the first law. Is it a little familiar? There are also two methods to determine the technical work. From the process equation we have. This means the technical work is gamma 0 times of the expansion work. Therefore, we have. Review the first law again. Is it a little familiar? Well, how about the heat during this process? We do not talk about the heat during this process. Can you figure out this value? It should be recognized that a reversible adiabatic process is necessarily isentropic, but an isentropic process is not necessarily a reversible adiabatic process. The entropy increase of a substance during a process as a result of irreversibilities may be offset by a decrease in entropy as a result of heat losses, for example. However, the term isentropic process is customarily used in thermodynamics to imply an internally reversible adiabatic process. Okay, that's all for this task. Thank you very much and see you next time.